Hey guys, I'm here back with another math video. Today we're going to be doing 2015 AMC10A, problem 25. Take a look at the problem, pause the video if you need to. Without further ado, let's solve it. So, let S be square of side length 1, 2 points are chosen independently at random on the sides of S. Probably the straight line distance between the points is at least 1/2 is A minus B pi over C. Where A, B, and C are positive integers with a greater common denominator of 1. What is A plus C equals C? Okay. Let's draw S. There's the square S. And 2 random points are chosen independently. And the straight line distance has to be at least 1/2. So, okay, let's just choose a point and label it A. Okay? Let's say A is right here. And I think what this will take is casework. Alright. So given that A is in an arbitrary location on the square, what's the probability that B is going to be at least 1/2? Well, case by case, so case 1, B is on the opposite side of A. So B is over here. Well, it's always going to be at least 1/2 if it's here, because obviously they're on the opposite sides of the square, and the square is side length 1, so obviously this is going to be at least 1/2. So if case 1, B is opposite of A, probability that B is op A equals 1/4, because there are 4 sides you can choose from, right? And the probability that B is going to be opposite of A is 1/4, and the probability that AB is greater than or equal to 1/2 is 1, because the probability is 100%. It's gonna if it's on the opposite side of A, it's definitely going to be at least 1/2. So that's case 1. Case 2. B is on same side as A. So, B is on the same side. Probability that B is on same side equals 1/4, because one side out of 4 of these you can choose from. What's the probability that AB is greater than or equal to 1/2? To do this, we need to use geometric probability, and that's essentially where you plot all the possible locations of A and B and see how many of those points are valid. So to visualize this, let's have a graph of A and B, and this graph will decide how far A and B are from this point. So how far they are from this point. We want B minus A absolute value to be greater than or equal to 1/2. Because if B minus A is greater than or equal to 1/2, that means AB is going to be greater than or equal to 1/2. Because their difference is equal to the distance between them. Their difference between their distances from this point is equal to this distance. So, let's see. So B minus A is greater than or equal to 1/2, which means that B minus A is greater than or equal to 1/2, or A minus B is greater than or equal to 1/2. This becomes B is greater than or equal to A plus 1/2, or B is less than or equal to A minus 1/2. And if we actually plot this on the graph, get something like this. So this is B is greater than A plus 1/2, and B is less than A minus 1/2. Pretty cool, I think. And actually, if you try out some points within these regions, you'll see. So like, say this point right here, let's say, let's just say A is 1/4, and B is 3/4. Well, no, sorry. Let's say A is 1/4, and I don't know, B is 7/8. That's this point right here. Well, if this is 7/8 and this is 1/4, obviously the distance between them is going to be greater than 1/2. It's going to be 5/8. So, totally the area of this region is 1 by 1, because A and B can be a maximum of a distance of 1 from this point. So it's a 1 by 1 square. And within this 1 by 1 square, these regions add up to an area of 1/4. It's 1/4 divided by 1, so it's 1/4. So the probability that AB is greater than or equal to 1/2 is 1/4. So that's how we do geometric probability. We basically plot the valid points on a graph and take it out of the total area of all possible points. Alright. Case 3. B is on an adjacent side. Probability that B is adjacent equals 1/2, because B can either be here or here out of 4 sides. What's the probability that AB is greater than or equal to 1/2? That's a bit harder. Let's think about it this way. If B is on an adjacent side, the straight line distance between them, given their distance from this point, let's say their distance from this point, let's say this is A, this is B, that's their distance. The D equals square root A squared minus plus B squared, right? And we want that distance to be greater than or equal to 1/2. So, we do the same thing actually. We graph it. Let's graph it over here. So A can be anywhere from here to here. B can be anywhere from here to here. So this is 1, this is 1. Now I want to graph A squared plus B squared is greater than or equal to 1/2. That's just graphing a circle. Squared equal 1/4. That's graphing a circle. And we know how to graph a circle. This is a circle of A squared plus B squared. Remember that it's greater than, so it's actually like this. And that's the region. That's where these that's geometric probability. All these points within the shaded region are totally valid because those points give where A squared plus B squared is greater than or equal to 1/4. So what's the area of this region, considering this is a square of 1 by 1, since A and B can be at max one distance of 1 away from the point? The area of that is just 1 minus pi over 16, because this area is pi over 16. So I think we have everything we need now. So case 1, B is opposite of A. That's a chance of 1/4, so that's 1/4. Case 2, B is on the same side as A. That's 1/4, and then the probability that greater than 1/2 distance is you have to multiply that by 1/4. Case 3, it's adjacent. Let me just calculate this right now. So it's 5/16 plus 8/16 minus 2 pi over 16. So it's 13 minus 2 pi over 16. And I think that's right. No, it's not right. Sorry. I miscalculated somewhere. 13 over 16 minus... Oh, sorry. Yeah, I did miscalculate. 1/2 times pi over 16 is not 2 pi over 16. That is pi over 32. So that becomes... that. So the answer should be 26 plus 1 plus 32 is equal to 59. So it should be A. I hope you found that interesting. Thanks for watching. 1 over x, because you divide both sides by the floor of x, plus 1 as you move this over, which is actually also equal to